Hello students, this is the Chapter 8 multiple choice review video. I'm going to be talking about all of the different multiple choice questions that you got on the website. Check these out right now. Here's the first question. A researcher plans to use a random sample of 500 families to estimate the mean monthly family income for a large population. It's talking about a 99% confidence interval based on the sample would be blank than a 90% confidence interval. Now keep in mind that the differences between these two confidence intervals is that they're going to have different critical values. When you look at the formula for confidence intervals, the part that says critical value is the part that's going to be determined by the confidence level. As the confidence level goes up, the critical value is going to go up, and as the confidence level goes down, the critical value is going to go down. A larger confidence interval, a higher confidence interval, I should say, is going to lead to a larger critical value. What that means for the overall margin of error is that as the critical value increases, the entire margin of error is going to increase. We're multiplying by this number, right? So that means to me that a 99% confidence interval is going to be larger than a 90% confidence interval. If the critical value goes up due to the percentage going up, then the margin of error is going to go up. So we're looking for a wider confidence interval. It's not going to be narrower, it's going to be wider. Now the meaning of a 99% confidence interval is that 99% of the intervals that we construct in the same way are going to contain the population parameter. Whereas with a 90% confidence interval, only 90% of the intervals that we construct in this way will contain the population parameter, which means we're looking for a wider margin of error, or a wider interval, I should say, and a smaller risk of being incorrect. We're talking about the risk of being incorrect as compared to 99 and 90. There's just, this is just a wider interval, so it's less chance of it being incorrect. There's more chance, in other words, of it having the correct population parameter within it. All right, moving on to question number 2. In a poll, for number 1, some people refuse to answer questions. For number 2, people without telephones could not be in the sample. And for number 3, some people never answered the phone in several calls. Which of these sources is included in the plus and minus 2 margin of error announced for the poll? And all of these sections 1, 2, and 3 are indicative of errors, but they're really sources of error due to sampling. They're not sources of error due to estimation or calculation. Some people refusing to answer questions, that's a source of error that leads to bias. People without telephones cannot be in the sample, that's going to lead to bias as well. And some people never answer the phone in several calls, that's another source of bias. The types of biases are listed, right? All of these sources of bias are going to affect your statistic. They're either going to make the statistic too large or too small. They're going to make it unreliable. However, none of these are going to be included in the plus or minus 2 margin of error. Keep in mind that the margin of error is based on only 2 things: the standard error of the statistic and the critical value. Both of these are calculated numbers, calculated values, and they're not going to be based on whether some people aren't in the sample or people never answer the phone. None of these are related to calculation error. They're all related to a different kind of error called sampling error. So it turns out that the correct answer is E. None of these are in the plus or minus 2 margin of error announced for the poll. All right, for question number 3, you have measured the systolic blood pressure of a simple random sample of 25 company employees. 95% confidence interval for the mean systolic blood pressure, we're talking about means, it's a good idea to underline there, is 122 to 138. So there's your confidence interval. Which of the following statements gives a valid interpretation of this interval? Now recall what that 95% is representative of. 95% says if we do this process many times, if we construct many confidence intervals, 95% of those confidence intervals, not of employees, not of samples, not of the population, 95% of those confidence intervals will capture the population parameter, and 5% will not. So for letter A, it says 95% of the sample of employees. We're not guaranteeing anything about the sample of employees. We're not guaranteeing anything about the population of employees. We are saying that if we do this over and over and over again, 95% of the confidence intervals contain the population parameter. This talks about probability, which we talked about in class. There's no such thing as a link between that 95% and a probability. And this is talking about 95% of the sample means, but remember, the confidence interval's job is very simple. Its job is to try to capture the population parameter, not a sample. So that's not the correct answer either. Moving on to question 4, a polling organization announces that the proportion of American voters who favor congressional term limits is 64%. They have a 95% confidence margin of error of 3%. Okay, so that means plus or minus 3 from that value. If the opinion poll had announced the margin of error for an 80% confidence level rather than a 95% confidence level, what would happen to the margin of error? Well, remember that the confidence interval is based on a statistic, a critical value, and a standard error of the statistic. Generally, we don't really talk about the statistic when we talk about how it gets larger or smaller because the statistic is just where it starts from. The critical value and the standard error tell us how large or how small the margin of error is going to be. Now, if our 95% confidence margin of error is 3%, that means the wings spread out to 3% above and below using 95% confidence. If I'm only dealing with 80% confidence, think about it. That confidence interval is going to go, that's right, it's going to go down. If the confidence interval is going down, or in other words, it's going from a confidence interval that kind of looks like this to a confidence interval that looks like this, that means that our wings are not as big. We're able to say that we are 95% confident that this interval captures the population parameter, but we're only 80% confident that this captures the population parameter. As we go down in confidence, the margin of error is going to shrink, and so too will the confidence interval overall. So that means the margin of error, based on all of this, if the critical value goes down, that margin of error is going to go down as well. So we're looking for less than 3%. So it's not equal to, it's not greater than, it's less than. What's the reason? Well, the sample size hasn't changed at all, right? The only thing that's changed is the confidence level. We require less confidence. That's what that means. So choice B is our answer. For number 5, a Gallup poll found that only 28% of American adults expect to inherit money or valuable possessions from a relative. That's kind of a low percentage. The poll's margin of error was plus or minus 3 percentage points at the 95% confidence level. What does that mean? Okay, I'm going to say what I think it means in my own words, and then I'm going to see which of these choices best fits. I know that the 95% confidence interval means if we create a confidence interval using the same methodology many times, over and over and over again, we can expect that 95% of those confidence intervals are going to be within 3 percentage points of 28%. In other words, the true population proportion is going to be between 25 and 31%. Okay? So let's see. We have the 25 and the 31%. It says Gallup can be 95% confident that between 25 and 31% of the sample expected inheritance. This one looks really good. However, it's not correct. Can you see why? Sample. We're not making any judgments on the sample for a confidence interval. Remember, the confidence interval's job is to identify where the population parameter is, not anything about the sample. 95% chance, we can eliminate that because we're not talking about 95% chances. Chance is sort of like a probability term. If Gallup takes another poll on this issue, that's another sample statistic. That's another sample proportion, so we don't care about that. Percent of all adults who expect an inheritance is between 25 and 31%. Wow, that sounds like a guarantee, and there's no guarantees in statistics. Turns out that it's letter A, and I'll tell you exactly why. The poll used a method that gets an answer. In other words, if we do this same procedure to get the same type of confidence interval multiple times, within 3% of the truth, there's our MOE, our margin of error, about 95% of the time. Yeah, 95% of the time, we are going to calculate a confidence interval that's going to be within 3% of the truth. That's the correct answer. Moving on to question number 6. Most people can roll their tongues. It sounds like this, but many can't. The ability to roll the tongue is genetically determined. So that means it's from your mom, your dad, or your ancient ancestors that came from wherever. Suppose we are interested in determining what proportion of students can roll their tongues. We're talking about proportions here. We test a simple random sample of 400 students. Wow, I don't know how you could convince 400 students to start rolling their tongues, and 317 can do it, and the other, 83 students are out of luck. The margin of error for a 95% confidence interval for the true proportion of tongue rollers is closest to. Well, how do you find the margin of error for proportion? Let's see. Let me see if I can try to remember. Oh, it's right here. Okay, great. The margin of error is this part of it, the critical value times the standard error of the statistic. So we can calculate that pretty easily by finding the critical value. We know we're dealing with proportions, so the critical value is always going to be z, and the standard error is going to be p hat times 1 minus p hat divided by n square rooted. And here are all my calculations. You can see that For the critical value, I found the z-score for 0.025. I used InNorm to find that. The 0.025 came from alpha over 2. We know 95% is between the sticks, so 5% is divided between the two different tails. 2.5% is in the lower tail, so that's how we got that 0.2025. 1.95966, or 996 rather, is the critical value. Then the standard error of the statistic is here. It's p hat times 1 minus p hat over n. That calculation is here. It's 0.02028. I multiply those two numbers together to get 0.03975. Be careful, 0.03975 is not closest to 0.03. It's closest to 0.04. Perfect. Question number 7. You want to design a study to estimate the proportion of students, another proportions question, don't worry, means are coming later, of students at your school who agree with the statement, the student government is an effective organization for expressing the needs of students to the administration. You will use a 95% confidence interval, another 95% confidence interval. Hint, we're going to be seeing that 95% a lot this course. And you want the margin of error, the MOE, to be 0.05 or less. Looks like we're finding a minimum sample size. Yep, that's right, minimum sample size required. This is one of those questions that you just need to use the formula for. And remember, the trick is this. We're going to be using the same confidence interval formula, which is statistic plus or minus critical value times standard error of statistic. And one thing that we don't have here is a p hat. Nothing here tells us the p hat. It just tells us the confidence interval and the margin of error. So what we're going to do is use a conservative estimate for p hat. Remember, that means that p hat is going to be 0.5, which means that 1 minus p hat is also going to be 0.5. Now here's the formula that you have to write out just as a quick understanding, or explanation rather. That 0.05 has the greater than or equal to symbol attached to it, and here's why. We want the margin of error, this part, this whole entire thing, to be 0.05, that's the equal part, or less. So we want this side to be less than this side. That's why we're using the greater than or equal to symbol. Every time you write an inequality, you should think to yourself, which side is okay to be bigger and which side is okay to be smaller? We want this side to be smaller than 0.05, so the Pac-Man eats the larger number. Solve this equation. It's not my job to show you how to solve equations because I'm your stats teacher, and you get letter C, which is 385. You're going to be eventually rounding that. I believe the answer comes out to 384 and change, but that's something for you to verify by yourselves. Question number 8. I collect a simple random sample of size n from a population and compute a 95% confidence interval for the population proportion. Again with the proportions. Folks, trust me, means are coming soon. Which of the following would produce a new confidence interval with a larger width based on these same data? Well, one thing that students sometimes think to themselves, oh, that's always going to be good, is increasing the sample size. However, increasing the sample size in this case is not going to make the confidence interval bigger. Think about it. When you increase the sample size, the thing that happens is your answer, your sample statistic, gets more reliable because you've tried to limit the amount of variability within the sample, right? If you pick one peanut butter jar and test its weight, it's going to be more variable than 10 peanut butter jars and testing their weight. And that's going to be more variable than 100 peanut butter jars and testing their weight, right? The more things that you have in your sample, the more accurate your sample becomes. So increasing the sample size is actually going to make that confidence interval go down. Let's see, using the same confidence level but computing the interval n times, that's nothing, right? Using the same confidence level is going to make the same margin of error, right? What we're going to be doing is proving the point that 5% of the intervals will not contain the population parameter. It's not that 5% of the intervals will be larger. That's not how that works. Nothing can guarantee absolutely that you will get a larger interval. That's ridiculous. That's poppycock. You control the confidence interval because you know exactly how it's calculated. Remember that confidence interval is statistic plus or minus critical value times standard error of statistic. One of these two things is going to have to go up if you want a larger margin of error. And guess what? As the critical value increases, the margin of error increases. That's a truism that we already talked about. Larger confidence level, that percentage, if you put it to 99%, that means you're spreading your wings farther or larger. One reason for using a t-distribution, finally we're talking about means, a t-distribution instead of a normal distribution to find critical values when calculating a level C confidence interval for a population mean. C just means any confidence level for a population mean, is that, well, think about why we use a t-distribution in the first place. In class, we talked about what to do when we were calculating critical values. what to do when we're calculating confidence intervals. And this confidence interval formula still holds true even though we're talking about means for number 9. This confidence interval formula deals with the critical value times the standard error of the statistic. When you're dealing with means, the problem with standard error of statistic is that the formula for standard error of statistic has the standard deviation baked into it. Here's what it looks like. If I was using the z critical value, I would have to use this formula to find the standard error of the statistic. The problem is that we don't know the standard deviation of a population. So we have to sort of guess it. We have to sort of like fake it a little bit. And instead of using this formula, we have to use this formula. Now, the good thing about using this formula is that you actually have the sample standard deviation just by calculating some sample statistics. However, the bad thing about this is that the sample standard deviation is a little bit crazier than the population standard deviation. Sometimes it's going to be big, sometimes it's going to be small. So the problem is that we can't rely on a z critical value to correctly encapsulate the confidence interval. So what we do is we use a t critical value. That t distribution is going to enable us to get that 95% or 99% or whatever percent confidence interval accurately. So here's the moral of the story. We can't use this one, essentially. This one is right out because when we're calculating a confidence interval for means, we don't have the population standard deviation. So letter B is our correct answer. Z requires that you know the population standard deviation. If we start using this, we have to start using the critical value named T. Number 10. Moving on to number 10, we have a simple random sample of 23 observations. That's 7 less than what we usually want for a normal distribution. Oh, but from a normally distributed population, here's what you got to remember. That 23 is not enough for us to say, well, the sampling distribution is going to be roughly normal. However, if we're drawing samples from a normally distributed population, we don't have to rely on this being 30 or larger. We don't have to rely on the central limit theorem. All right, what critical value are you going to use to obtain a 98% confidence interval for the mean of the population if the sigma, the population standard deviation, is unknown? Well, there's the trick. As soon as we know that the population standard deviation is unknown, we know we're going to be using t. So the way I usually like to draw something in the t family, in the t distribution family, is like this. Not exactly looking the same as a normal distribution. I've got kind of a flattened peak. All right, we need 98% in between the sticks, so that's between here and here. So there's our 98%. That means each of the tails is going to have 1% respectively. Here's our 1%, and here's our 1% down here. So what we're going to be doing is using inverse t to find this critical value, the critical value representing the boundary between the 98% in the middle and the 1% in the tail. So this value is going to be found by using inverse t. But unlike using z as a critical value, we're not just going to put in the area under the curve. T distributions are a family of distributions, so there's infinite numbers of t distributions. So what we need to do is also input another piece of information. That's right, the degrees of freedom, which is based on n. Degrees of freedom is equal to n minus 1. So our degrees of freedom here is 22. Let's type in that 22 right here. And we use our calculator to figure this out. We'll bring the trusty calculator over. We're supposed to do inverse t, so second distribution. And keep in mind, if you don't have inverse t in your calculator, you just need an updated version of that TI software. The area under the curve is 0.01. The degrees of freedom is 22. We'll just paste that bad boy right in there, and we should get 2.50832. All right, 2.50832, so about 2.5. Oh, look at that, 2.5. But don't get trapped. 2.50832, 2.508 is the one we're looking for. So there's a correct answer. And let's circle that. And I just dropped my phone. Perfect. You know what? I could edit that out, but I think I'll leave that in there. All right, question 11. We're looking at a quality control inspector measuring the salt content in milligrams of a random sample of bags of potato chips from an hour of production. Spoiler alert, it's going to be too much. There's too much salt in chips. Which of the following would result in the smallest margin of error in estimating the mean salt content, mu? We're looking for a small margin of error. I hate to keep bringing it back to the confidence interval formula, but we're going to use it again. We want this entire thing, this margin of error, to be as small as possible. So we need this critical value to be small. We could have the standard error be small as well. which means if we want the standard error to be small, we could get the sample size to be larger. There's a couple of different ways that we can get this margin of error to be small. All right, let's do a little work. Between 90% confidence and 90% confidence, those are the same. All things being equal, a sample size that is larger is going to have a smaller margin of error. So 25 is right out because 50 is bigger than that, and the 90% confidence is the same. Now, a n equals 50, 90% confidence, and an n equals 50, 95% confidence, the 90% confidence is going to be smaller. Why? Because 95%, that larger confidence level, is going to mean larger wings. So 95% is out as well. And then between B and C, well, 90 versus 95%, we assume that this one is going to be, we know that this one's going to be smaller. And then a larger sample size leads to a smaller margin of error as well. So both of these indicate smaller margin of error. Both of these indicate larger margin of error. So this one's out. The last one says n equals 100 at any confidence level. I'm always hesitant to say anything is correct when it's got that any in there. It's really trying to shoot the moon. But what we can do is we could try to calculate it out. But it doesn't seem to have any data here, so we can't really calculate it out. Well, let's see. N equals 100 at any confidence level. Well, what if the confidence level was 99% or 99.9%? If it's that large of a confidence level, if it's that large of a percentage, that means that the wings are going to spread really far. Remember, we're trying to get at the smallest margin of error. So at any confidence level, no way. 99 or 99.9 or 99.99% confidence levels, those wings are going to be super big. The margin of error is going to be super big. So choice B is our only choice. It's got the 90% confidence, which is the smallest confidence level, and n equals 50, which is the largest sample size without going crazy. All right, moving on to question number 12. Scientists collect data on the blood. Wow, that would be weird. Cholesterol levels, milligrams per deciliter of blood, of a random sample of 24 lab rats. Okay, 24 is our N. 95% confidence interval for the mean blood cholesterol mu is 80.2 to 89.8. So they've already made us a confidence interval. How nice is that? Which of the following would cause the most worry about the validity of this interval? Well, let's knock off the ones that are immediately obvious as to be wrong. You do not know the population standard deviation sigma. Well, that's okay, because in this case, when we're calculating a confidence interval for means, we're not using Z anyway, we're using T. And T is specifically designed because we don't know the population standard deviation. So that one's okay. The population distribution is not exactly normal. Newsflash, folks, a population distribution is never going to be exactly normal, right? We can say that it's approximately normal, but we don't care if the population distribution is exactly normal, because most of the time what we could do is we could assume that if we meet the other conditions, it's going to be normal enough, right? So we don't need it to be exactly normal. Who cares about that one? Moving on to a stem plot of the data shows a mild right skew. It's okay that there's a mild, right? It says mild here, skew, because even if it's mildly skewed, right? If the distribution kind of looks like this, like it's got a little bit of a tail. This is actually even more than mildly skewed. But anyway, even if it's got a little bit of a tail like this, it's normal enough, right? Mild skew doesn't mean it's abnormal. It's normal enough that we could use these same procedures effectively. I know that this is a distribution, like a line graph and not a stem plot, but you get the idea. There is one thing that worries me, and there's one thing that should worry you as well. There's a clear outlier in the data. As soon as we can prove that there's something with the data that's clearly not normal, not just mildly not normal, not exactly normal, none of these, but as soon as we can prove that there's a clear outlier in the data, there's going to be stuff that goes on that is against our conditions, right? One of the conditions is that we have to have normal or large counts. Right, this 24 is not big enough for large counts, so we need the distribution of the population, or at least the distribution of the sample, to be normal. If there's a clear outlier in our sample data, we can't really use that data the same way as we would any other forms of data. That's why we do the conditions in the first place. As long as there's a clear outlier, as long as it's not normal, then we can't use that procedure. That would cause us to worry about the validity of the interval. Validity of an interval is checked by those three conditions: normal large counts, 10%, and random. None of these would be a problem. Well, we already eliminated that because we said that A is a problem. Question 13, a Gallup poll, keep talking about Gallup polls, interviews 1,600 people. Of these, 18% say they jog regularly. So of these 18%, this is a p-hat. right? It is a sample proportion. The news report adds, the poll had a margin of error plus or minus 3 percentage points, another plus or minus 3, how about that, at a 95% confidence level. You can safely conclude that, well, what can you safely conclude? Well, typically we look for the language if we take many samples. Oh, here's one. If we took many samples, 95% of them would find that 18% of the people in the sample jog. Whoa, 18% of the people in the sample? First of all, we don't make assumptions about samples. And second of all, only 18% and not 18% plus or minus 3. This one's doubly wrong. And in this case, 2 wrongs don't make a right. Here's another one that we can cross off instantly, letter B. Why? Because there's no promises, there's no guarantees in statistics. It is certain to be between 15 and 21%. Hit the road. We can be 95% confident that the sample proportion is kept. Oops! Sample proportion. Remember, we're looking for capturing a population proportion with a confidence interval, not a sample proportion. Nice try. 95% of the population. Well, it's not really talking about 95% of the population. It's talking about 95% of the confidence intervals that we can make using this procedure. It's not talking about 95% of the population, so that one's wrong too. Turns out the correct answer was right under our nose the whole time. 95% of all Gallup poll samples, yes, I know it talks about samples here, but keep reading. 95% of all Gallup poll samples like this one give answers, confidence intervals, within 3% of the true population value. That means, in other words, if we take many samples and we make many confidence intervals, 95% of these samples, in other words, of these confidence intervals, will give answers within plus or minus 3 of the true population value. In other words, 95% of them are going to be capturing that true population value with that 3% wing. All right, number 14. The weight in pounds of 3 adult males is 160, 215, and 195. The standard error, oh my gosh, the standard error of the mean of these 3 weights. Don't worry, there's a formula for it. Man, what a lovely formula. In fact, I'm not even going to show you how to use this formula. I'm just going to tell you the correct answer because all you got to do is plug the numbers in. No big deal. Question 14 is D, 16.07. What did we do here? We took these 3 values. We found the sample standard deviation by putting them into the calculator and doing stat calc 1var stats to get that standard, that sample standard deviation. Then we divided by the square root of 3. Why 3? There's 3 things here and the sample size is 3. No big deal. In preparing to construct a 1 sample t interval for a population mean, 1 sample t interval for a population mean. All right, everything checks out so far. Means usually means we're using t intervals anyway. Suppose we're not sure if the population distribution is normal. Oh, okay. We don't know if the population distribution is normal, which means we have to try to pass that normal large counts condition some other way. In which of the following circumstances would we not be safe in constructing the interval based on a random sample of size 24 from the population? Okay, size 24, that's not big enough to meet that large counts condition. That's not big enough for large counts. So we can't say the t procedures are robust, so they're always safe. They're not always safe. When this number is less than 30, we can't use it necessarily. What way can we say that we're not going to be safe constructing the interval based on that simple random sample? Well, let's see. Well, if we make a stem plot of the data and it's roughly bell-shaped, that's a good sign. That actually tells us that we can assume normality because at least our sample is normal. So I'm going to say A is not correct, right? If it's roughly bell-shaped, it's normal enough so we can assume normality. A histogram of the data shows slight skewness. Hey, slight skewness, that's good enough for me, guys. As long as it's slightly skewed, it's mostly normal. So we're going to call this one A-OK as well, which means we're not saying that it is not safe. A stem plot of the data has a large outlier. Uh-oh, your alarm bell should be going off. As long as you see this word large outlier, that indicates that your data in your sample is not normal. It's got that outlier in it, which means it doesn't follow all the regular laws of normality, which means we can't use a t procedure on it. The sample standard deviation is large. I mean, it's okay that the sample standard deviation is large. Sometimes a normal distribution has got a large standard deviation. Depending on how large the values are, that's okay. So we don't really mind too much about a sample standard deviation being large. Question 16, we're coming into the home stretch. Many television viewers express doubts about the validity of certain commercials. In an attempt to answer their critics, Timex Group USA wishes to estimate the proportion of consumers who believe what is shown in Timex TV commercials. Okay? P represents the true proportion of consumers who believe what they see in Timex commercials. What's the smallest number of consumers? Oh, another smallest number question, a minimum number of sample size question. So remember from the previous problem, that margin of error is going to involve a calculation with p hat times 1 minus p hat divided by n. Oh, we did forget one thing here. We are going to need that z star in there because we're talking about proportions. All right, so now we're going to fill out this formula using p hat and 1 minus p hat. We're using the conservative estimate here of 0.5 for both of these. And at this point, it's just a question of can you crunch these numbers and solve for n. Here's what you get for n. All right, we get the answer of 665 is greater than or equal to n. That means n has to be less than or equal to 665. Looks like the one we're looking for is 650. Moving on to question 17, or question 1717, if you don't copy edit your materials, you want to compute a 90% confidence interval for the mean of a population with unknown population standard deviation. Unknown population standard deviation means you're going to be using a t, and proof positive, you're going to be using t. If the sample size is 30, the degrees of freedom is 29, which means we're going to bring over the calculator and see what it says. All right, a 90% confidence interval means our alpha value is 0.10, alpha over 2 is 0.05, so I'm going to go to second distribution, go to inverse t, put in 0.05 as our area under the curve, and remember our degrees of freedom is 29. Answer, well, I have to click enter one more time, don't I? And another time, don't I? It's 1.69913. 1.69913. That's the correct answer there. 1.699 for question 17. All right, moving on up to question number 18. In question 18, a radio talk show host with a large audience is interested in the proportion P of adults in his listening area who thinks the drinking age should be lowered to 18, as it is in some places around the world. To find this out, he poses the following question to his listeners. You think the drinking age should be reduced to 18? In light of the fact that 18-year-olds are eligible for military service. So I want to be careful before we actually answer this question. This way of asking this question does have a source of bias in it. This is sort of a leading question, right? It gives information within the question that is intended to have the question answered in a certain way. But anyway, he asked listeners to phone in and vote yes if they agree the drinking age should be lowered, and no if not. Of the 100 people who phoned in, this is only people that responded, right? So a little bit of response bias. 70 answered yes. So we have 70 people here that answered yes, and 100 people total. So our p hat is 0.7. Which of the following conditions for inference about a proportion using a confidence interval are violated? Okay, so we need to check violations to the conditions. And remember, there are 3 conditions we have to check. And those 3 conditions are as follows. The random condition, the 10% condition, and the normal/large counts condition. Remember that random asks you were the subjects selected randomly. The 10% condition asks whether the sample is less than 10% of the population. And then normal large counts condition asks you whether, in this case with proportions, n times p hat is going to be greater than 10, and n times 1 minus p hat is going to be greater than 10. So we can pretty easily verify the normal large counts condition by performing those 2 checks. 70 is greater than 10 and 30 is greater than 10. We can also pretty easily address that 10% condition. There's probably more than 1,000 listeners. It does specify he's got a large audience. Large is a subjective term, but the reason they threw in that large was to say that it's probably more than 1,000 listeners. But the random condition is really sticking in my craw a little bit. And the reason why is because it says that the people who are responding are listeners that are asked to phone in and vote yes or no. But these are folks that aren't selected randomly. They self-selected themselves to respond. So looking at the conditions here, number 1 says the data are a random sample from the population of interest. This is simply not true, right? In this case, that is violated. Number 2, n is so large that both n times p and n times 1 minus p are at least 10. This one we checked already. That's the normal large counts condition. And then the population is at least 10 times as large as the sample. That's the 10% condition. We got that one too. So the only one that's violated is number 1, which is the random condition. Moving to question 19, a 90% confidence interval for the mean mu of the population is computed from a random sample and is found to be 9 plus or minus 3. So 9, that's your point estimate, your statistic. It's the sample mean. And then 3 is the margin of error. Which of the following could be the 95% confidence interval based on that same data? Well, it's 9 plus or minus 3, which means the margin of error is 3 for 90%. The only thing that changes from the original part of the problem, where it says 90% plus or minus 3, to the new clause, which is 95%, is that the confidence level increases. A confidence level increase means that the margin of error is going to increase as well. So 9 plus or minus 3 is going to have to become 9 plus or minus something else, right? So it can't be that, and it can't be that, and it can't be that. These are all values that are either equal to or smaller than the margin of error. I know that at 95% confidence interval, an increase of 5% in your confidence level means that the margin of error has to be larger. So D is going to be the correct answer here, which could be, we're only looking for which one could be. You don't have to do a whole lot of math for this one. Any of the above answers could be the 95% confidence interval. No way. We can't have 1.96 because that's a smaller margin of error than the plus or minus 3. 90%, 3. 95%, it's got to be bigger. Number 20, suppose we want a 90% confidence interval for the average amount of books, average we're talking about means, right? And 90% confidence interval spent on books by freshmen in their first year at a major university. Spoiler alert, it's going to be a lot. The interval is to have a margin of error of $2. Based on last year's book sales, we estimate that the standard deviation of the amount, the standard deviation of the amount spent will be close to 30, What's the number of observations required? Closest to, so this is another minimum sample size question. So let's substitute some numbers into that margin of error calculator. We know that the margin of error is going to be 1.645. That's the critical value times 30 divided by radical n. That is the standard error. How'd I get 1.645? Easy. I know that I'm working with means. So what I'm going to try to do is use t. However, read this question a little bit carefully. It says, based on last year's book sales, we estimate that the standard deviation of the amount spent will be close to $30. So based on last year's book sales, that sounds like a population to me. So the value that they gave us, this 30, even though we don't know the exact value, we're going to treat it like a population standard deviation. The standard deviation of the amount spent all of last year is close to 30. So in this case, since we have a good idea of what the population standard deviation is, we don't have to use t. We're actually going to use z. So going to second distribution, we're looking at inverse normal, and we're doing inverse normal using area of 0.05. Of course, that's alpha over 2. We're talking about 90% confidence interval, so we got 0.05 in one of the tails. And 0 and 1 are the mean and standard deviation. That gives us 1.645, right? So that's that value that we're going to plug into our equation here. And I'm sorry, inequality here. Now all we got to do is solve it for n. All right, so that means that the next step is going to be to divide both sides by 1.645, then make this square root of n come to the other side, and then divide both sides by whatever 2 divided by 1.645 is. Listen, we're getting lost in the weeds here. You need to do this algebra by yourself. Here's what you get. At the end of the day, you get 608.85109. Looks to me like that number of observations required is going to be closest to 609. And remember, all throughout this calculation, we're supposed to round to a bunch of decimal places. You want to keep as many decimal places as possible. Take 5 decimal places if you want that 5. All right. Next, a telephone poll of a SRS, remember that simple random sample, of 1,234 adults, ooh, a very nice number there, found that 62% are generally satisfied with their lives. Oh, so that's about 2/3. The announced margin of error for the poll was 3%. Does the margin of error account for the fact that some adults do not have telephones? Now think about what this question is asking. Does the margin of error, which is a calculated value based on the critical value and the standard error of the statistic, account for the fact that this part, some adults do not have telephones. This part, some adults do not have telephones. This is a source of sampling bias. Think back to the beginning of the video when we talked about that. A source of sampling bias is not taken into account with the margin of error. Margin of error is just a calculated value. It doesn't take into account errors in design of the study. So that means the answer for 21 is going to be, it's not yes, it's going to be some form of no. Now this one says no, the margin of error includes non-response but not undercoverage. Well, that's not true. Non-response is a type of sampling problem, so that's not included in margin of error. The thing that margin of error addresses is sampling variability, right? Like it uses the critical value to sort of simulate that sampling variability or address the sampling variability. The margin of error includes sampling variability, but nothing related to non-response or other types of bias. And last but not least, question number 22. Census Bureau report on the income of Americans says with 90% confidence, the median income of all U.S. households in a recent year was $57,005, with a margin of errors of 742. All right, so we're talking about medians, not means and not proportions, but that's okay. Let's not panic yet. We can still interpret this in terms of what a confidence interval does. It predicts a population parameter, in this case the population median, or really it tries to capture that population parameter. So let's remember what confidence intervals do, or specifically what they don't do. This says 90% of all households has income in the range, blah, 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 blah. That's not what it does. It doesn't say 90% of all the population has that. It says if we do this a lot of times, 90% of the confidence intervals that we make will contain the true population, in this case, median. For letter B, we can be sure, oh boy, sure, no guarantees in statistics. 90% of the households in the sample interviewed by the Census Bureau had incomes. It's not talking about 90% of households. Remember, it's talking about 90% of confidence intervals, so that's not it. The Census Bureau got the results 57,005 plus or minus 742 using a method, okay, we like it so far, that will cover the true median income 90% of the time when used repeatedly. Oh my gosh, music to my ears. If we do this method a bunch of times, we're going to cover the true median income 90% of the time. That's exactly right. And then 90% of all possible samples, that's not what it's talking about. 90% is the number of, well, actually, wait, 90% of all possible samples, so this is good so far, of the same size, this is good so far, will result in a sample, oh, okay, this is the part that fails it. A sample median that falls within 742? No, we need a population median to be in here. All right, so the correct answer is choice D. Checking that, yep, that's right. Wow, I love getting it right. Anyway, here are all of the answers all on one slide, so you can check your answers over one more time. All right, this was the video on the Chapter 8 multiple choice review. Good luck studying.